Okay, our first relationship that we're going to talk about is Boyle's law. This is our first gas law that we're going to discuss in this chapter, and it's a simple relationship between pressure and volume. So here we are with the volume and pressure, and that's our of a gas. And the bottom line is it's a inverse relationship between pressure and volume. So we can write the equation as we see here. Oh, we also need to make sure that we have temperature constant, so we need to have a temperature constant. And then when we do that, we have pressure times volume, and we write this, where K is a constant. And K remains a constant, so if it's constant, then you can write another equation where it's P1 V1 equals P2 V2, because we know that if a constant will always remain a constant. So if the constant was, let's say, 2 is always going to be 2. So if you have one thing equal to 2, then another thing will equal to 2. So then the two things are equal to each other. So we have P1 equals V1, P1 V1 equals P2 V2, and that's the more useful equation because it allows us to solve for different conditions. So if we're given P1 and V1 and we're given the pressure of the new condition, we should be able to solve for V2, and vice versa. If we're given V1 and P1 and we given the volume of the new condition V2, then we should be able to solve for P2. And the relationship can be very well shown up here if you look at this curve here, where if the pressure is very high, the volume is very small, and if the pressure is very low, the volume is much larger. And if you look at the kinetic molecular theory of gases, that you can understand why, because as you decrease the volume of a container, remember the gas will fill its full container, you have the number of particle collisions on the walls of the container will increase. You have the same mass in there, right? And you're reducing the volume and the same temperature, so the kinetic energy of the particles are the same. So they will be striking the walls of the container much more frequently than they would if the container was very, very large. And so therefore, as we mentioned in the slide before, an increase in pressure will result, right? Because pressure, remember, is equal to force times a unit area, and that's the pressure. And as you put more and more collisions in there, more and more force in that area, the pressure will increase. And vice versa, if you increase the volume, right, then you'll have a lot more mean distance for these particles to travel, so the collisions will go down, and the pressure should drop also. So let's see how we can apply Boyle's law to these set of conditions here and demonstrate from a concept what's happening. So we have a pressure of a gas at 760 torr, and we're going to change that pressure to 380 torr. So if you do the math real quick here, that's a twofold, or we're halving the pressure, a twofold decrease in the pressure. And we're going to keep the constant temperatures because we need to do that for Boyle's law. Else, if we don't keep the temperature constant, then Boyle's law does not apply. And then we want to know what the new volume of the gas is if we do the reduce the pressure by 2. So we already know that P times V is a constant, right? So if we know that if we look at a set of equations here, so if P goes up, then we know that V must go down to maintain that constant, right? And it's just as simple of if you have, let's say you had 3 here, and then you multiplied by 2 to give you 6. If you increased the P to make that 6, then you'd have to decrease with that one to be 1 to get you the same 6, right? So that's basically what we're doing here. So that's the concept, right? It's a mathematical concept. You can see that. So if you increase the P, then the V must go down, as we showed before, right? So if that goes down, then the P goes up and the volume goes, and vice versa. If the P goes down, as in our condition, then the V must go up, right? And to give that same K, because these K's are the equal, right? So P1 V. So in this particular case, this is our condition that we're looking at, we have the volume must be increasing to satisfy the conditions. So let's look at another example of Boyle's law and how we can actually apply it to a real world situation. So now we have a gas sample that has a volume of 25 milliliters and a pressure of 1 atmosphere. And if we double the container size to 50 milliliters and keep the temperature constant, we want to understand what the new pressure will be. So we always want to try and write our general equation first. So we have P times V equals K, right? And so we also know that P1 V1 equals P2 V2, and so we know, and that will also equal K. And the thing we can do here is now so we're wanting to look for the new pressure, so that'll be P2. So this is what we're going to call this P2. And so we'd solve for P2 right now just to make all this easier to look at. So we have P2, and we're just going to make this P1 over here V1, and then we're going to divide that by V2, because that's what we're basically looking for. We want to understand with this, and we assume that we have all these things given above. So then we can put in our numbers here. So let's just do that real quick. We're looking for P2, and P1 is going to be 1 atmosphere, and I'll work on the units in a minute. And then we sample in milliliters, so that's 25. And then we have on the bottom 50. Again, I haven't written in the units yet. We'll do that in a second. And so if you do this math, it's 1 times 25, which is 25, and then divided by 50. So P2 is going to be equal to a half, so 0.5, right? And we have 3 significant figures, so we have to add 3 zeros. And our units for pressure, since we started out here, was atmospheres. It's going to be atmospheres, right? Because the milliliters here and the milliliters here will cancel. And so our P2 is 0.5 atmospheres. And so that's how we got that answer. So here's another one of these concept thought equations again, and we're looking to what happens to the pressure on a given mass of gas is increased, and then what will the volume response be, again at constant temperature. So let's just always write our general statement, which is a P times V equals K, right? As K, and so we want to know if the given mass, if the pressure of a given mass is increased, so P is going to increase, and then we want to know what the volume of the gas would be. So everything else is the same, and constant is the same. So in order for this to work, then we know that the volume must decrease, right? Because if P increases according to this equation, then the volume must decrease to maintain that constant. So our answer would be that if the P is increasing, then the volume is going to be decreasing, right? If the pressure on a given mass is increased, the volume of the gas will decrease, right? Putting more pressure on it, we're compressing it, so it makes sense. Okay, for our last thing on Boyle's law, let's just look at one more example here. And then a cylinder with a tightly fitted piston is shown in the diagram below. As the piston moves downward, the number of molecules of air in the cylinder, and then that's what they're looking for, A decreases, B increases, or C remains the same. And we know that it should remain the same because we're not really should be losing any air. So as long as there is no escape of material from here, so let's just draw a bunch of particles in here real quick, right? These are our gas particles. They're just all over the place. Make that more dense. As long as the gas particles are not escaping, so no escape, right? There's no escaping of the gas particles. As we constrict them more, or put less volume in them, they're going to spend more time hitting not only each other but hitting the walls more frequently. And just remember that the pressure equals the force times the area, and the force is basically, in this case, the number of collisions. I'm just going to put that first, number of collisions was C times the frequency, or that is the frequency. So the number of collisions, right? the number of collisions per unit area. So as the number of collisions increases, because as a proportion of the number of collisions per area, as the temperature stays the same, but we constrict the volume, then the distance that the particles have to travel before they hit another wall is getting smaller and smaller, and they have the same kinetic energy by the temperature, so they are hitting the walls more frequently. Therefore, the pressure must increase. So as we look at the answers here, this increases, and it makes sense because if you've ever tried to compress a gas, a closed system gas, at some point it starts to get very, very hard to do this because the pressure that the gas is exerting upwards while you're trying to push it down has increased.